Hello, I'm Nosunhan of Optical Frequency Com Spectroscopy team of IBS CNSD. I'm going to talk about my published paper related to pump-proof spectroscopy. The title is Time Resolved Spectroscopy of thioflavin T solutions, asynchronous optical sampling method with two frequency up-converted modular lasers. Dual frequency comb spectroscopy applies the asynchronous optical sampling scheme. It requires two optical frequency combs with slightly different repetition frequencies. In this case, the spectra of two optical frequency combs have different comb line spacing in the frequency domain. The interference fringe generated by these two combs in the time domain produces a radio frequency comb with a line spacing of the tuning frequency. For the measurement of a linear spectrum of the sample using the frequency comb, the repetition frequency and carrier envelope offset frequency have to be highly stabilized. In our team, we reported these spectroscopy studies to these journals. They explain the dual frequency comb spectroscopy in the spectral range of near IR and mid IR respectively. In contrast, when we measure the time-dependent intensity, the optical phases of the two laser fields do not matter. We called it incoherent Azoff scheme. In this case, only the repetition frequency is highly stabilized and the modular lasers are synchronized to the same time base. Using these useful applications, we have studied time-resolved spectroscopy, which are termed Azoff-TA, and frequency-resolved Azoff-TA. In this video, I will introduce the incoherent Azoff-based NUV-NUV and NUV-NIR pump-proof measurement and the twisted intramolecular charge transfer process of the photoexcited thioflavin T molecules. First, we generated NUV radiation sources by frequency conversion. To find the optimal length L for a given spectral bandwidth theta K, we performed theoretical calculations solving a series of nonlinear coupled wave equations and simulated the spectral evolution of the second-order generation field and the nonlinear conversion efficiency of each frequency component in the broadband pump pulse. Based on our simulation, we found that the spectral bandwidth delta lambda of the SHG beam decreases with increasing thickness L, but the output power increases with L. Additionally, in the critical phase matching configuration, the incident angle of the input beam changes the center frequency and the spectral bandwidth of the generated NUV beam. Using these simulations, we generate the pump beam with a narrow bandwidth of 1162 wave number and output power of 1 nanojoule per pulse, and proof beam with a broad spectral bandwidth of 2300 wave number in the red box of the experiment setup. The center frequency of pump and proof beam are optimized to the absorption of the target molecules ratio in this spectra. Over the past 3 years, we have experimentally demonstrated time and frequency resolved transient absorption, time resolved impulsive stimulated Raman spectroscopy, and two-dimensional electronic spectroscopy only in the near IR region. Here are both NUV Azoff-TA and frequency resolved Azoff-TA measurements are for the first time carried out for THT molecules in solution. For the NUV Azoff-TA, the time delay between the pump and probe beam is scanned automatically. The pump and probe pulse trains were non-collinearly focused at the sample in the flow type cell with a thickness of 100 micrometer. At the sample position, the single pulse energies of the pump and probe beams were 0.6 nanojoule and 12.5 picojoule respectively. At the interaction with the sample, the intensity of the probe beam was measured in the positive port of the last detector. After any generation, the remaining fundamental beams in the NIR region were used to generate optical signal that are the sample generation of the pump and probe beams. It has the FWHMM or 13 femtosecond. The frequency reserved age of TA spectroscopy involving interferometric detection of the pump probe signal field, amplitude and phase, is capable of measuring both the transient absorption and reflection spectra simultaneously. Similar to age of TA, the pump and probe pulses from modular laser 1, ML1, with a repetition frequency of 18 megahertz and ML2 with a repetition rate of 18 megahertz plus DTD frequency interact with chromophore in the solution, which produces the third order polarization with a wave vector identical to that of the probe beam. Then this pump probe signal field is allowed to interfere with the local oscillator beam that is time delayed by tau from the probe beam, where the time delay is generated by using a mechanical delay stage whose moving period is synchronized to the optical trigger signal. Using these new spectroscopy tools, we investigate the photophysics of thioflavin T in various solvents. As shown in this figure, the previous studies revealed that thioflavin T, the photoexcited thioflavin T in the Francondo state, relaxed to a locally excited state, LE state, before the intermolecular charge transfer occurs. The THT molecule in the locally excited state can emit a photon to return to the ground state or undergoes the transition to a twisted intermolecular charge transfer state. THT molecules are dissolved in solvents containing chlorine atoms, chloroform, and dichloromethane. The fluorescence quantum yields become notably high compared to those in non-chlorinated solvents, such as methanol, even though the viscosity of the chloroform is similar to that of the methanol. In this respect, we measure the frequency reserved age of TA of THT molecules in alcohol and chlorinated solvents. The frequency reserved TA spectra of THT in 2-propanol are shown here. The three represented TA spectra at the delay time is 100, 1000, and 2000 femtoseconds are also plotted here. At a short time, below 1 picosecond, there appears a positive transient absorption signal in the wavelength region below 450 nanometer, which is called excited state absorption, induced by the absorption from a lower excited state to a higher excited state. The negative TA signal originated from ground state bleaching for the depopulation of ground state by post-excitation appears in the whole spectral range of the probe beam. We used an optical filter center at 450 nanometer to measure the time profiles of the positive ESA contribution and the negative GSB contributions to the TA signal separately. The slowly varying time profiles could be fitted with two exponential functions. For the GSB signal, the fitted rise and decay times were found to be 3.6 and 28 picoseconds. Those of the ESA signal are 4.2 and 42 picoseconds respectively. After removing the slowly increasing and decaying components in the GSB and ESA signal, we could extract the oscillatory features in the signal. The coherent vibration spectra were obtained by transforming the oscillatory GSB and ESA signals in the previous slide. Since the red side of the ESA band spectrally overlaps with the blue side of the GSB band, the oscillatory signals associated with pump excitation induced vibration wave packages could be the mixture of the excited and ground state contributions in general. However, we found that the two coherent vibration spectra associated with GSB and ESA appear to be quite different from each other. These experimental results are compared with quantum calculation. It is the 500 wave number mode that is the characteristic vibration associated with the excited state. Although a notably strong peak at about 200 wave number appeared in the coherent vibration spectra of GSB, multiple peaks in the low frequency region below 200 wave number and strongly vibronic coupled modes in the high frequency region around the 500 wave number are observed in the coherent vibration spectrum of ESA. These experimental observations, together with quantum chemical calculation results, led us to conclude that the TH signal at short wavelengths below 450 nanometer mainly originated from the ESA contribution. We also measured the ESA signals of THT in methanol and chloroform and obtained the Fourier power spectra of the oscillation components. The coherent vibration spectrum of the excited THT in methanol is quite similar to that in propanol. In contrast, the coherent vibration spectrum of the excited THT in chloroform shows distinctively different features, which are the absence of 200 and 520 wave number peaks in the coherent vibration spectrum of THT in chloroform. Actually, the coherent vibration spectra were obtained by Fourier transforming the TH signals at short times. Therefore, the vibronically coupled modes identified from the coherent vibration spectra are associated with the initially excited state, not fully relaxed TICT state. These results suggest that these two modes, whose vibronic coupling strengths are substantially small for THT in chloroform, could be related to the internal rotation, twisting motion, with respect to the central carbon-carbon bond. The transition from the initially excited state to the THT state is driven by the sorbation of the product, THT state, by polar sorbent molecules surrounding each photoexcited THT molecules. Therefore, the sorbent reorganization energy associated with the generation of the THT state is an important quantity determining the chemical equilibrium between the locally excited state and the THT state. If these two modes, 200 and 520 wave number, have distinctively different sorbent reorganization energies in alkyl sorbents and chlorinated sorbents, the driving force inducing the transition from the initially excited state to the THT state could strongly depend on sorbents. Therefore, the lack of two strongly vibronically coupled modes in the coherent vibration spectra of THT in chloroform should be an important clue to understanding why the population of the THT state of THT in chloroform is substantially smaller than those in alcoholic sorbents, which in turn enhance the fluorescence contaminant of THT in chloroform. To obtain more information on the excited state dynamics of THT into propanol, we additionally carried out NUV pump and NI-approved edge of steam measurement. At short times below 5 picosecond, the NUV pump and NI-approved spectra of THT in propanol show a broad ESA band covering the entire spectral range of the NI-approved beam. The experimentally observed ESA band in the NIR region was assigned to the transient absorption of the from quantum excited state and locally excited state. After 5 picoseconds, a broad stimulated emission band from 750 to 900 nanometer was observed. These results suggest that the TH spectrum at long delay times could be assigned to the stimulated emission from a relaxed S1 state and THT state. The time profile of NUV pump NI-approved signal in the wave range from 850 to 900 nanometer is also shown here. It could be fitted with 2 exponentially rising components and 1 slowly decaying component. Based on the analysis of previous reports and our experimental results, the rapid decrease in the ESA signal and the slow rise and decay of the stimulated emission signal can be interpreted as the relaxation of the S1 state by absorption and population transfer to the THT state and subsequent lifetime decay of the generated THT state, respectively. Finally, to address the sorbent dependence of the vibronically coupled modes with frequency of 200 and 520 wave number, we carried out quantum chemistry calculation of the ground state and excited state with density function theory and time-dependent DFT method. The experimental observation is that the 2 vibronically coupled modes with the frequency of 200 and 520 wave number become weak in the coherent vibration spectra of THT in chloroform, chlorinated sorbent. This result means that the vibration reorganization energy of these 2 modes in the excited state of the THT in chloroform are much smaller than those in methanol and 2-propanol. In other words, the molecular structure of the THT excited state in chloroform and the strength of intermolecular interaction between THT and chloroform molecules might be different from those in non-chlorinated sorbents such as methanol and 2-propanol. We examined the vibrational transition dipole moments of 4 different vibrational modes. We calculated dipole moments for varying displacement along their vibrational eigenvectors. It turns out that the 2 modes with frequency of 214 and 526 wave number have notably large transition dipole moments. Our experimental results suggest that the reorganization energies of the 2 vibrational modes exhibit large electric dipole moment changes are relatively small in chloroform compared to those in 2 alcoholic sorbents. Therefore, the intermolecular charge transfer driven by the sorbation of surrounding polar sorbent molecule may not occur effectively in chloroform. The initially excited THT in chromophore reacts to the locally excited state, but does not undergo the transition to the THT state because the lack of stabilizing observation process. So here we show that NUV pump and NUV probe and NUV pump NIR probe as of TA are useful techniques for studying the intramolecular charge transfer process of THT in solutions. These experimental and quantum chemistry calculation results indicate that the sorbation process is not sufficiently efficient in chloroform so that the THT state is not substantially populated, and thus the fluorescence from the locally excited state, not the THT state, is efficient. We anticipate that the present experimental work will stimulate further theoretical and computational studies on these molecular systems to elucidate the difference in the intermolecular interactions of the photoexcited THT and surrounding sorbent molecules.